1.3 is a thing of beauty, and let me show you why that is the case. So consider the product 1 plus 1 over 2 multiplied by 1 plus 1 over 3, and lastly multiplied by 1 plus 1 over 4, so on and so on. Each factor in the product is of the form 1 plus 1 over n, for which n is greater or equals to 2, as we can clearly see from the first term that is the case. And then the question is saying determine all the values of n for which the product will be an integer value. Determine all the values of n for which the product will be an integer value. So this product as it is very hard to digest, but we can change it a bit. Let me show you in what way we can change it. So let me just drag these down and show you a couple of things. I want to drag these down. There we go. So instead of having 1 plus 1 over 2, let's just put that in our calculator. I get 3 over 2. So here the first term that I have is 3 over 2, right? And then let's move to the second term. 1 plus 1 over 3, that is 4 over 3. And then the third term, 1 plus 1 over 4, that is 5 over 4, right? 5 over 4. Let me rewrite that. So these are the terms of the product, not the terms of the sequence. Let me put it here so that I can show you something. And then this pattern goes up until 1 plus 1 over n, right? Of which we do not know. So the last term here that we have is 1 plus 1 over n. But we can do the same thing for that term. Well, not the same thing, but we can also rewrite that term. Let me show you how. 1 plus 1 over n. 1 plus 1 over n is the same as n plus 1 over n. Because if we give both those two terms on the numerator, a denominator of n would end up with 1 plus 1 over n. So instead of writing 1 plus 1 over n, we can write n plus 1 everything over n. But it does not end there. It does not end there. There's another layer of complexity that I want to introduce here. So that is the last term, right? For some n terms, right? That is the last term. So that is the last term. But I want us to think about the term that comes before this one. I want us to think about the term that comes before that one. So the term that comes before this one is supposed to be, so this is the last term. So I want us to concentrate on the term that comes before that one. The term that comes before that one, it should have a numerator of n minus 1, right? Plus 1, because it is the term that comes before n. So it must be n minus 1. So on the denominator also, we are supposed to have n minus 1. We are replacing n with n minus 1. So let's put that term together with the other terms. So we are saying that the first term is 3 over 2. 3 over 2. It is followed by 4 over 3. And then after that we have 5 over 4. And then we have some terms. Before the last term, n minus 1 plus 1 is just n, right? So we have n divided by n minus 1. And then after n divided by n minus 1, we have n plus 1 divided by n. That's what we have. So let me erase this and show you what happens here. You can see for the first 3 terms that 3 and 3 will cancel out, right? After that, 4 and 4 cancels out. 4 and 4 cancels out. If you were to add the 4th term there, you would see that 5 and 5 would cancel out. So ultimately, we are left with 1 over 2, right? After 3 and 3 cancels out, we are left with 1 over 2 up until these last 2 terms. But with the last 2 terms, n and n cancels out. That's easy to see that n and n cancels out. So we have some 1 over n minus 1, and lastly, the last term that we have is n plus 1, right? So that's what we're going to have. So let's see how these two terms behave. 1 over 2 and n plus 1. Let's see how they behave. We want the product to be an integer, right? An integer is a number that is not a fraction. It's a whole number, right? So when can these be whole? When can we multiply these two things and have a whole number? It's when n plus 1 is even. Because take a look at this. If n plus 1 is odd, we're going to have 3 over 2. And that is not whole, right? If n is odd, we're going to have 5 over 2. And that is not whole. But if n plus 1 is actually even, then we can have 4 over 2, which is 2, right? We can have 6 over 2, which is 2. So how can we achieve that? If n is equals to 3, our condition is satisfied, right? Because we're going to have 4 divided by 2. If n is equals to 5, we're going to have 6 divided by 2. If n is equals to 7, we're going to have 8 divided by 2. So on and so on. So n can be 3, 5, 7, 9, up until infinity, right? Some infinity odd number so that our product can be an integer. So there we go.